Well, this is take 2 on 10.2 notes. Thank you for those that let me know that the first video was very hard to follow, and I'm going to hope for better results on this one. So if you listen to the first one, this might be slightly different, but I'll try to teach the same lesson again. So in 10.2, we're doing find arc measures. An arc comes from a circle. So if you have a circle, any part of that circle that is on the outside here, so any portion of this outside part is called an arc. So that's what we're looking for today in their measures. Just as a quick note, all measures of a circle are up to 360 degrees. All of our measures will be in degrees. All right, so we're going to start our definitions here with central angle. Just a quick reminder on all these vocab. All mine are filled out already. Don't be afraid to pause your video to fill yours in before you move on. So we're on central angle, and this is an angle whose vertex is in the center of the circle. So if I go to the center of the circle and make my angle using this center point as the vertex, this angle right here is called the central angle. And I do want to stress the vertex is at the center of the circle, because when we move on to 10.4 and 10.5, we're going to have other angles in a circle whose vertex is moved around. So it's important to realize this is the vertex at the center of the circle. And just a quick heads up on this one. So if we have this central angle here, if it happens to be, let's say, 48 degrees here, we're going to learn down at the bottom here a little bit that this angle, the arc measure on the outside, will also be 48 degrees. So they are the same measure. All right, so we have different kind of arcs on a circle. Our first one we're looking at here in the next definition is a minor arc. This is the part of an arc where it's less than 180. So this 48 degree arc you see right here, this could be a minor arc. And we compare that to a major arc down here beneath. And the major arc is the part of the arc that is more or between 180 and 360. So if we take the rest of this circle all the way around this way, this whole arc right here, this would be a major arc. And just a quick reminder too, if you think about it, if a whole circle is 360, I could subtract that 48 that's part of that minor arc there, and I could get a measure of 312 degrees here for my major arc. So we'll notice the measurements on a major arc are somewhere between 180 and 360. We have a semicircle for our next definition, and the semicircle here is an arc with endpoints whose endpoints are on the endpoints of a diameter. Remember from last section, a diameter is a chord that goes through this center, so it goes on both sides of the circle. The endpoints are on both sides. There's my diameter, and then this arc right here is the semicircle. So exactly half of my circle is a semicircle. And because it's exactly half, we know that that's going to equal exactly 180 degrees because it's half of my 360. So going on to our definitions, the measure of a minor arc is the measure of its central angle. We talked about that, the 48 degrees and the 48 degrees. And we'll notice that a minor arc will always be less than 180. The measure of a major arc will always be more than 180 because it's more of that circle. Moving on down here, congruent circles. These are two circles that are congruent if they have the same radius. We're going to see that on about the third page of our notes, and I'll stress the rules on that one. And congruent arcs are arcs from the same circles as well. I do want to step back on these congruent circles. These circles have the same radius. If you remember back for congruent triangles, they had to have congruent angles and congruent sides. Well, if you think about a circle, there are no angles on the circle itself, and there are no sides on the circle itself. The only sort of measurement on any circle is the radius. So if you have circles that have the same radius, then they will be congruent circles. And then again, like I said, the congruent arcs we'll look at on page 3 of our notes. All right, down here at the bottom, talking about the measuring of arcs. We're going to kind of mix between what I have in the margin and what I have here in the box. The measure of a minor arc is the measure of its central angle, and I did say that up above when we did the definition. So you'll notice here I have a central angle of 50, so this arc over here is 50. All right, the expression MAB is read as the measure of arc AB. The measure, M says we're going to make it equal to something, and it's going to be some kind of number. When you only have two letters, always go to the shortest distance between those two letters. Clockwise, counterclockwise, it doesn't matter. You want the shortest distance. So if I see A and B here, my arc AB is between A and B, the shortest distance between there, and that becomes a minor arc. If we want you to go the opposite way, we're going to need to give you three letters like this one, and you kind of follow them like a dot to dot. You do the directions they tell you. Let me change colors so it stands out here. It says the measure of ACB. So I start at A, I find C all the way over to B, and there's my major arc. So major arcs will be named with three letters. Minor arcs can be named with two or possibly three letters, but your arcs are usually named with either two or three letters each time. If it's two letters, always the shortest distance between those. Back over here to our box of notes, the measure of the entire circle is 360 degrees. The measure of a major arc is the difference between the 360 and whatever the minor arc is. We did that up top with the 48 degrees here. If my minor arc is 50, I can do 360 minus 50, and I can get that angle of 310 degrees, sorry, not an angle, an arc, and that 310 goes all the way around here for ADB. And back in the finish of the box, the measure of a semicircle is always going to be 180 degrees. So page 1, a lot of definitions, a lot of just making sure we understand the terminology. Let's move on to page 2. All right, on page 2 here, you'll notice we have a circle, and we're going to work on finding the measure of each arc, and we're going to tell if each arc is a minor arc, a major arc, or a semicircle. So we see that we have circle C. I want to point out to you that they do tell us that DF is a diameter. That's important to know because that means it's splitting that circle in half, which also means it's going to split all of that 360 degrees around the outside in half. So quick reminder, 360 on the full circle. You'll notice that we have a central angle in here of 117. If the central angle is 117, this arc that closes it off right here between D and E will also be 117. If I want to find the other side of that same diameter going across, I know that diameter cuts it into 180, so I can do a 180, losing my space here. 180 minus my 117 will leave me a 63 degrees. Doesn't want to write for me. So I know that I have 63 over here. And then, of course, over here, that full is 180 because it's the full semicircle. So I'm looking at just the picture first. Now let's go back and answer the questions they asked me about this picture. All right, we want the measure of DE. First I find D, I find E, and I go the shortest distance between those. Because that looks like it's less than half the circle, I know that I have a minor arc. And I already labeled that as well, that if my central angle is 117, my arc measure is also 117 degrees. So it matches that angle of angle DCE. You'll notice on the second angle, they call it by three letters, which is fine. And the second arc, I keep calling them an angle, it's an arc. This arc DFE, to find it, we're going to use a little bit of dot to dot. So I go to D, I'm going to the direction of F, and then to E. And you'll notice it finishes the circle from that minor arc I did earlier. So this is definitely a major arc. It's more than half of the circle. And I'm going to find it just by doing 360 minus that 117 that we did before. And 360 minus 117 is 243 for my big major arc there. And the last and final arc they asked me about on this circle is arc DEF. Notice DEF has the same letters as DFE, but because they're in a different order, I have a different arc that I'm talking about. So again, follow that dot to dot. If I go to D, then to E, then to F, I realize I've done half my circle. So that is definitely a semicircle. And we know all semicircles are exactly 180 degrees. All right, moving on to our checkpoint. It says find the measure of arc RTS in the diagram at the right. Three letters, let's play dot to dot with it. I started R, to T next, and finally to S. And I notice as much of that circle there that I'm definitely looking at a major arc. And because it's a major arc, I'm going to do 360 minus the minor arc. Well, if this was 45 inside here at central angle, it's 45 on the arc as well. So I'm going to subtract my 360 minus my 45. And it looks like my arc measure is 315. Looking at this next postulate, 23 here. Arc addition postulate. It's not a difficult one to know. Probably you could have figured it out without a postulate. It says the measure of an arc formed by two adjacent arcs, remember adjacent are two that are touching side by side, one right after the other, is the sum of the measures of the two arcs. So if I'm looking for arc ABC, notice here ABC in that dot to dot, it says I can stop and I can just do the measure of AB, the first part, and add it to the measure of BC, the second part. So if I don't have, especially on those major arcs, if I don't know maybe the minor arc that goes with it, I can just add pieces as well. And you don't have to just add 2 pieces. You could add 3 pieces or 4 pieces, whatever works best for your problem. So let's go ahead and look at our chart here on example 2. Normally we would call this a pie chart, and in some ways it looks a lot like a pie chart. I will tell you most pie percent. And when I look at this one, it definitely looks like I'm not using percentages, but I'm looking at degrees. 55 degrees, 140 degrees, 60 degrees, 105. I'm hoping if I add all those up, they should add up to 360, my full circle. And let's go ahead and start with the first one. It says, find the measure of arc BD. I find B and I find D. Am I finding my arc to the left or my arc to the right? It doesn't tell me, so I have to remember my rule of thumb, which is always go the shortest distance. Always try to find the shortest distance between those two letters, because that's going to be my minor arc. Because I'm looking for the shortest, I'm going to go to the left here. And it looks like I have a couple arcs to add together. My checking there is 55 degrees. My saving is 105 degrees. I'm going to add those together for 160 degrees. On my second question, B here, I have arc BCD. Start at B, I go towards C, and then to D. And that actually is the exact opposite of from what I used before. So I can always use my rule there, 360 minus that 160 I got earlier, and I get 200 degrees. Or if you're like me, sometimes I look and I say, well, it's 2 sections. One was 140, one was 60. If I add them together, I get my 200. So really, either way you look at that, you get the same answer. So it's really your choice which way you can visualize that better, or which one works better for you. Either one of them come up with the same answer. Moving on to page 3 here. All right, on page 3, I did warn you about this, where I said we would talk about this when we did the definitions earlier, congruent arcs. So before we look at the problems, let me give you a couple rules for congruent arcs in the margin. Congruent arcs need 2 things, and I want to make sure when you're finding those, you check both of these things. Okay, one thing is they need to have equal measures. So if you think they're going to be congruent arcs, they both have to have the exact same number in their measures. And the second thing we have to check for, they either need to be from the same circle or from congruent circles. Okay, and we'll kind of show you as we go through these examples what I mean by that. But I do want to stress to you, do the double check every time that you make sure both properties are there to make it congruent arcs. So let's go ahead and look at A here. Our job here is to try to see, is arc BC and arc DE, are they congruent? So we have 2 things we're checking. Do they have equal measures? And do they come from the same circle or congruent circles? Well, on BC, I see a central angle of 75, which means this arc is 75. On DE, I see a central angle of 75, so this arc is 75. So I would definitely say we have equal measures. I see the same number on both of them. Now I look for the second one. Do I have the same circle or congruent circles? Well, it's obvious to me on this one, they're both in the same circle. So since they're in the same circle and they're equal, I would definitely say my two arcs are congruent. All right, let's look at B to see a little bit of change here on this. So on B, once again, I'm looking at arc AB here and arc CD here. And it looks like they both come from the exact same central angle. So that's kind of obvious that both of them have to have an arc measure of 80. So they definitely have the same measure. So that fills this requirement up here. But then I look at their circles. They're definitely not from the same circle, so no congruent circles, or same circles. And my circles, when I look at them, it's quite obvious they're different sizes. One's smaller and inside the other one. So they are not from the same circle. The arcs of the circles, they are not congruent. That's what we want to put right there, because they are arcs of circles that are not the same size. All right, let's look at example C now. I have arc FG and arc HJ. Are they congruent? So again, we're looking for two things. Let's look at equal measures first. In this circle that has FG here, I see a 90-degree angle as my central angle, which means my arc is 90 degrees. When I look at the arc with HJ, I see a 90 degrees angle there, which means HJ is a 90-degree arc. So definitely I have the same measures again, so I fill this first one, equal measures. They're definitely not the same circle, but let's check to see if they're congruent circles. On the top circle, I see a little congruent mark on that radius there by the F, and I also see the same congruent mark on the second circle by H. So that means the radii are the exact same length, which means they are in this congruent circles. So since we have congruent circles and we have equal measures, definitely those two arcs are congruent. Moving on to my checkpoint here. Checkpoint 2 here goes back to my picture from the last page, kind of that pie chart we were looking at. I'm going to just try to kind of sketch a new one here. So I had my circle. Wow, that's a terrible circle, but it'll do. I have A here, B here, C here, and D here. So I'm going to kind of put my pie pieces in here. All right, not perfect, but it'll do for the example so we know what we're looking at. Let me get some numbers in here too. 105 over here, 60 down here, 140 over here, and 55 up here. Okay, that should be enough to get me where I need to go for my examples. All right, for example 2, it says for A, find the measure of BCA. All right, so I need to go to my circle. I'm going to play a little dot to dot with BCA. Start at B, go all the way to C, and keep going until I meet A. So I'm going over here. Definitely looks like a major arc. I know they didn't ask me for that, but it's nice to just kind of keep my brain there so I know my number has to be larger than 180. And it looks like I used all the circle except for that 55. So probably the easiest way to find this one is do 360 minus 55, and that leaves me with a 305 on that one. All right, same circle, different arc this time for B. I'm looking for the arc of ABC. Once again, same 3 letters, but because they come in a different order, it's going to be a different arc. I'm going to start at A, I'm going to go to B, and then to C. This one looks like kind of close to half the circle. I'm going to do the math first here. I get a 55, and I'm going to add it to that 140 to include both of my arcs, and that looks like it makes a 195. So if I wanted to name that one also would be a major arc. And of course that one was easier to find with adding just the way the picture was set up. All right, example 3 down here. In the diagram at the right is arc PQ, here's arc PQ, congruent to arc SR. Here, explain why or why not. Well, I know I have 2 things I want to check. One thing I want to know first is, do we have equal measures? Well, I'm going to be honest, they didn't give me any numbers, but I do see a congruent mark on by PQ and a congruent mark by SR. So that must mean that if my angles are congruent, my arcs will also be congruent. So I definitely know I have congruent arcs. You know what, let me rewrite that in a little different way. They're asking me if I have congruent arcs. I don't want to get mixed up here. Let's just say I have equal measures. That's probably a better way to say it than to talk about the arcs. So right now I have equal measures. And remember, I have a second check. Does it come from the same circle, or do they come from congruent circles? Well, this one definitely comes from same circles. So it means I have a check on both things I need to check for. But so between those two, that means yes, I have PQ congruent to SR, because I do have both parts of my arcs and both rules fit. All right, it looks like the book wanted us to stop here, but I have another problem I really want to kind of challenge us with, so let's turn to the last page of our notes here. All right, we're doing a little bit of coordinate geometry here. We'll put a circle on the coordinate plane. A couple things they tell us here is K is at the origin. So there's my 0, 0 right there. And it looks like I have 4 other ordered pairs. A, I don't know what it is. B is at 5, 4, and C is at 4, 5. So there's my circle. And they want me to find the arc measures on circle K. So I want to know how big these measures are. So looking at A, I have the measure from B to A. So here's my arc that goes from B to A. I want to find its measure. Well, I know it's less than 90 degrees. And I will tell you, don't pull out a protractor. I'm somewhat known for not drawing to scale, so there's a good chance a protractor won't help me. I need to use some kind of mathematical rule. Well, I know from this section that if I find this angle here, this is my arc, and if I find this central angle, it'll be the same thing as the arc. But once I find that angle, I like to usually stump you in class with this, but since no one's here to really answer my questions, I guess I have to answer my own. So I guess the question is like, I don't know, I have this ordered pair. What does that ordered pair means? It means I came across 5, and then I went up 4, and I reached that point B. I went straight across and straight up. That kind of makes a nice 90 degree. I think I have an right triangle here. Can I find a missing angle on a right triangle? Chapter 7 says I can. So I'm going to come down here so I can see this work a little bit better. It looks like I have this triangle, 5 here, 4 here. It's a right triangle. And if I can find this angle here, I could find my arc measure up on my circle. All right, remember from chapter 7, I like to often call my angles theta or something Greek. You can call it X. You can put an A here or something, I don't care, but I like to call mine theta. And it looks like, just kind of a quick reminder from chapter 7, on my right triangle here, across from my right angle is a hypotenuse. Across from my angle here is the opposite side. And touching this angle is the adjacent side. So when I think of a little bit of SOHCAHTOA that we used back in chapter 7, it looks like if I have the O and the A, I have a little TOA that should help me solve for that angle. So TOA, T stands for tangent. So I'm going to do tangent of angle theta equals the opposite, which is 4, over the adjacent, which is 5. And again, thinking back on chapter 7 rules, I really want that theta by itself. It has a tangent connected to it. Well, what undoes tangent? Well, usually inverse tangent is its opposite. So if I can take the inverse tangent of the left side to cancel these, I have to take the inverse tangent of the right side, and theta should equal inverse tangent of 4/5. All right, I'm hoping you have a scientific calculator handy. For many of you, that could just be your phone. Turn it sideways so you get all those functions on your calculator. Remember, no matter what kind of calculator you're using, make sure it is in degree mode, and you're going to find that inverse tangent button. Remember, it's almost always a second button. Even on your phone, you might have to hit second, and then that tangent inverse should kind of show up. If you don't have a phone that can handle that and you don't have a scientific calculator, if you're on my Google Classroom, go down to find the folder, or it's probably way at the bottom that says Geometry Resources, and I should have a link to a scientific calculator on that, or just Google free scientific calculator on your search engine, and you should be able to find a scientific calculator. So I hit inverse tangent of 4/5, and my handy dandy calculator says that my theta should equal 38.7 degrees. All right, so that's my B here, 38.7 degrees. I'm sorry, that's A. So this green arc right here is 38.7 degrees. So drawing that triangle using a little trig work from back in chapter 7 helped us find that angle, because remember, if this angle here is 38.7, my central angle, then my arc is also that. All right, now that we know how to do A, B should be a little bit easier. B says find the arc from C to A. I go to C, come all the way to A. I'm finding this arc. Well, I know my answer should be bigger than 38.7, less than 90, but I would like a better and more exact answer than that. So once again, I keep thinking, if I can find my central angle, I can find my arc measure. So I'm going to use the same process I did for A, and I noticed that for my ordered pair 4, 5, I went over 4 and up 5, and it made a nice right triangle. So let me put my B over here. So now I have kind of this tall triangle. It went over 4, up 5, but I still want to find this angle down here. So the setup is still going to be similar. I have my opposite, I have my adjacent, so I'm still going to set up a little tangent work. So I have tangent of this theta equals its opposite, which is 5, over its adjacent, which is 4. Once again, to get theta all by itself, I need to move that tangent. The only thing that undoes tangent is inverse tangent. What do I do to the left side? I do to the right side. These two cancel. Theta is going to be the inverse tangent of 5 over 4. Run that through your calculator again. Make sure it's in degree mode. And I believe when you run that through, you should get about 51.3. I hope you can somehow read this. So that looks like CA is 51.3. So this whole angle right here is 51.3. Sorry, not angle, arc. I need to be careful on my vocab here. 51.3 degrees for that big arc. All right. Moving on to arc CB. C's up here, B's here. This is a very short arc. It does not use that x-axis down there. We can't draw a nice right triangle because it doesn't go all the way to the bottom, so we can go across and up like we did on the other two. But if you think about it, I had a short arc of 38.7. I had a bigger arc of 51.3. How do I find this little part in between here? It's a little subtraction work. 51.3, subtract that 38.7, and I should find arc CB. When I subtract them, I get about 12.6. So about 12.6 there on the end, and if I add that to 38.7, it makes the whole 51.3. All right, 3 arcs down, 1 answer to go. Use a color maybe I haven't been using here. I'm going to use a purple here. It says find AK. Here's A. Here's K. AK here. I don't know what A's coordinate is. AK. Oh, that's the radius of the circle. Here's another radius of the circle. Here's another radius of the circle. And I know from the rule, all radii in the same circle are the exact same length. How could I find the radius of the circle? Wait, it's the hypotenuse of this triangle. It's also the hypotenuse of this triangle. So for D here, let me think. I have a right triangle. One of the legs is 5 and one of the legs is 4. If I look at the one from B, one of the legs is 4, one of the legs is 5. We know those can flip-flop, so it really doesn't matter. I'm looking for this hypotenuse over here. Right triangle, I know two sides, I'm missing one. I bet Mr. Pythagoras could be a good friend of us here. How about a little a squared, b squared, c squared? Remember, our trick on all these is which one is c. C always needs to be the one across from the right angle. So it looks like the c is my x. And my a and my b can flip-flop, a 4 in one spot, a 5 in one spot. It doesn't matter which is which, and let's do the math. 4 squared is 16, 5 squared is 25. X squared is x squared. 16 and 25 makes a 41. And it's time for us to take the square root to solve for x. Nothing perfect about this number. Square root of 41, handy dandy calculator, should get us about 6.4 on that one. Now just a quick note on this. Some of you may have said, wait, I see a 4 and a 5. Shouldn't I get a 3, 4, 5 triangle if that's something? Well, one thing I want to remind you, if you have a 3, 4, 5 triangle, the 3 and the 4 have to be the legs. Since 5 is one of my legs, I can't have a hypotenuse of 5, so I can't have my 3, 4, 5 triangle. So on this triangle, I have a 4, 5, 6.4 triangle. Not a nice Pythagorean triple. All right, so there is our notes again on 10.2. So I changed things up a little bit. Sometimes the book gets a little hard to use right now, especially where we can't be together. So I'm going to opt not to use the book homework. And you have a 10.2 worksheet that you should be able to find on Google Classroom. Try it. I will tell you that there are two tricky problems with the clock problems. I will tell you one of them has a decimal answer. So I'm going to let you kind of try to play with it a little bit, figure it out, and I might do a tutorial again tomorrow on how to do some of those clock problems. And if you have problems with this video, if you make it this far, let me know and I'll redo it again. Thank you.